In this presentations, we are going to discuss about paging. So the contents are paging, structures of page table, swapping. The examples. The first one is the Intel 32 and 64-bit architectures and ARMS versions 8 architecture. The objective is to provide a detailed descriptions of the Intel Pentium, which supports both pure segmentations and segmentations with paging. The paging. Here, the physical address space of a process can be non-contiguous. So the process is allocated physical memory whenever the latter is available. So avoid the external fragmentations and avoid the problems of varying size memory chunks. So divide physical memory into a fixed size blocks and frames. So the size is a power of 2 between 512 bytes and 16 megabytes. So divides the logical memory into blocks of the same size called the pages. Keep track of all the free frames. To run a program of a size n pages, so we have to keep n frame is a free for load the program. So set up a page table to translate logical to physical address. So packing store likewise split into pages still have internal fragmentations. So in this address translation scheme, the address generated by the CPU is divided into page number and page offset. Okay, actually the CPU is generated a logical address. Okay, so this address is divided into two parts, page number and page offset. So in this page number used as an index into a page table, so which contains base address of each page in the physical memory. Then the page offset combined with the base address to define the physical memory address that is sent to the memory unit. For given logical address space is 2 and the space size is 2. So in this paging representations is the CPU give a logical address that is subdivided into two parts, P and D. Okay, address, page number and the offset value. So page number it defines the which page and here the offset value is D. So from this page number we can get F frame address F. So the F and D is an physical address. So afterwards that the frame and D offset value D and the frame address is F. So using F and D we have to make a process in the main memory, that is in read or store operations. So in this paging model of logical and physical memory. So in this logical memory, page 0, page 1, page 2, page 3 are available. In this page table, 0 as the value is in 1 and the page table content is in 1 has a 4. Okay, then 3 and 7. So that is in frame number indications. So in that when we move to the physical memory, the frame number 1 is in page 0 in the logical memory. Okay, the frame 4 is indicate the page 1 in the logical memory. So like that the frame 3 indicated 2, then the frame 7 indicate 3. Then paging example, the logical address n is equal to 2 and m is equal to 4 using the page size of 4 bytes and the physical memory of 32 bytes, that's in 8 pages. Okay, so consider this logical memory. Okay, the logical memory, so it is a 0 to 15 pages. Okay, then the page table as 0 to 3 with the frame representation is 5, 6, 1, 4 corresponding values. Okay, in the physical memory, that is a frame, the corresponding frame is indicated to the page value. So the paging in the paging, calculating the internal fragmentation. So page size is 2048 bytes. The process size 72,766 bytes. Then 35 pages plus 1086 bytes. So internal fragmentations of the 2048 minus 1086 is 962 bytes. So worst case fragmentation is 1 frame. On average, fragmentation is 1 by 2 frame size. So the small frame size is describable. But each page table entry takes memory to track. So this page size growing over the time. Here the pages 14, 13, 18, 20, 15 are waiting to allocate free frames. Okay, so in this new process, the frame slot only the 4, 0, 1, 2, 3. So the 14 is allotted, 13 allotted, 18 and 20. These are placed in the particular frame in the main memory, but the 15 is only in the free space that is not allotted. So the implementations of page table. Page table is kept in main memory. So page table base registers points to the page table. Page table length registers indicates the size of the page table. So in this scheme, every data instructions access required two memory access, one for the page table and one for the data instructions. The two memory access problems can be solved by the use of the specific fast lookup hardware catch called translation look-aside buffer. It is also called associative memory. So in this paging hardware with this TLP, so the processor give a logical address with the two part, okay, page number and the offsets value. So it is a page number is referred in the page translations table, okay, and in the page number with the corresponding frame number is get from the translation table. So from the frame number and the page number, we form a frame number, that is an frame address. Okay, so from the F we give a physical address with the offset value. The structure of page table. Memory structures of paging can get huge and straightforward methods. Consider a 32-bit logical address space as a modern computer. Page size of 4 kilobyte. The page table would have 1 million entries. If each entry is a 4 bytes, each process 4 megabytes of physical address space for the page table alone. So don't want to allocate the contiguous in main memory. So a simple solution is to divide the page table into smaller unit, hierarchical page, hashing page table and inverted page table. So in this hierarchical page table breaks up the logical address space into multiple page tables. A simple technique is a two-level page table. So we then page the page table. So here the outer page table is indicate the page number in the page table, so that can be referred in memory. So in this two-level paging examples, a logical address is divided into two parts, a page number and page offset, isn't it? So since the page table is paged, the page number is further divided into 10-bit page number and 10-bit page offset. So here the page number furtherly divided into two parts. Okay, so the logical address is now follows P1, P2 and D. Okay, there are three parts. So where P1 is the index to the outer page table and P2 is the displacement within the page of the inner page table, so known as forward mapping page table. So in this three level paging scheme, again the outer page is number is subdivided. The hashed page table, the common in address space 32 bits. A virtual page number is the hashed into page table. This page table contains a chain of elements hashing to the same locations. Each element contains the virtual page number, the value of the mapped page frame, a pointer to the next element. So virtual page numbers are compared in this chain searching for a match. If a match is found, the corresponding physical frame is extracted. So variations of a 64-bit address is a cluster page tables, similar to hashed, but each entry refers to several pages. So the hashed page table where the logical address P and T apply the hash functions to the page number. So what's the result of the hash functions, that is take as the value for the frame address. Okay, that is to be added with the offset values that generate a physical address. So the inverted page table. So rather than each process having a page table and keeping track of all possible logical pages, track all physical pages. One entry for each real page of memory. So entry consists of virtual address of pages stored in that real memory locations with the information about the process that owns that the page. So they decreases memory needed to store each page table, but increases time needed to search the table when the page reference occurs. So use hash tables to limit the search. Okay, so it is in most a few page table entries. So the translations tables can accelerate access. So in this inverted page table architecture, the CPU generated logical address has the additional identifications information, that's in PID and E. So both are generated from the page number. Then it is the indications and identifications in the page table. From this we get the value of I, the I and D merged. Finally we get the physical address. The final process is swapping. So the process can be swapped temporarily out of the memory to the backing store and then brought back into memory for continued executions. If the amount of memory space or the short term executions, it is not record, it is not available, so in this time the swapping is most useful. The total physical memory space of process can exceed physical memory. The backing store first disk large enough to accommodate copies of all memory image for all users must provide direct access to these memory images. So schematic view of the swapping, the operating systems and the user space where consider the backing storage as a process. So if the process P1 is not frequently used, then it is a back out, that is swap out to the backing storage. Then the process 2 is the need to execute for the further fast processing, so that is swap in or back in to the user space. So that is the process of swapping. So swapping with paging, so which page is not and which page is not used continuously, so that pages are correspondingly swapped in and swapped out. Okay, thank you.